90,000 cases and even more. So, so it's not good. And it seems that we cannot go outside. We cannot go really outside the campus. So you can go, but people are not going much. But it seems that it will be like this for another 5-6 months easily. So.
Yeah. I was reading in the media this morning that maybe we would have maybe at least 1 year more like that maybe.
Oh.
I hope, I hope not, but well.
Oh, that is bad. So you can go, but people are not going much. But it seems like. Sorry.
Yeah. So for your place, is how the situation is?
In Paris?
Yes.
Oh, so we all have to wear masks, of course, inside the university, also outside in the street. The only exception is that when you are alone in an office, like I am. So now I am allowed to wear to take off the mask, but this is the only exception. And this is fortunate because give a Zoom seminar with the mask is not that easy, probably.
So most of the faculties are coming in the institute.
So sorry.
Most of the faculty are coming in the institute usually.
Oh, yeah. Almost everybody. Yeah. Mm-hmm. And what about you?
So few people are coming, but most of the people are taking classes from their home, online classes.
Yeah, by Zoom?
And in Zoom or in Google Meet. And there are the administrative staffs, they are coming 3 days in a week.
Okay.
So that's the situation.
Okay. So half of the week, let's say you are staying home, right?
Yes, they are staying home, but most of the faculty, but since we are usually in the campus, we are in the campus housing. So for our case, the situation is different because we are going every day to the office.
I see. You live on the campus. Yeah.
Yes, usually we live in the campus.
I see. Is it a very big campus where you are?
Kind of 200 acres kind of thing. So it's big.
Oh, it's huge.
Not as big as IITs.
Oh.
For example, for us, it is 1,300 acres. It's very big.
It's very, very big. Yeah. Okay.
You visited sometimes in Chennai, right? Long back?
Sorry?
You visited Chennai, right?
Oh, I went in Chennai quite long time ago, something like 10 or 12 years, something like that.
Is it in Chennai? In Chennai IITs or?
Exactly. It was there. Exactly. Yes. You were there, maybe?
No. I am not there. I actually, when in 2010, that IHP that you organized, that Trimstar or control, in that time I have visited in the IHP. I am not there I am not in Chennai IIT, but I know that you have visited there.
Okay.
You told me in that time, I think, when we are in IHP, that you came sometime in Chennai.
But sorry, I did not understand you. You said you came to IHP in 2010?
Yes, and you are the organizer in that time.
So we met.
One of the organizers.
So we met. I'm sorry, I cannot remember about that. But so okay, fine.
Can you once share the screen just to try the option?
Sure. Here it is. Okay. Can you see it in a good way?
Yes.
Okay.
Yes.
I can even try to put it.
Control L.
Okay, it is now full screen. Is it of good quality for you?
For me, it is a good quality.
Yes.
Perfectly fine.
So that's very fine. Okay. It is strange. Today in France, we have a very hot temperature. It is something like 35 degrees Celsius. And we are very not used to that kind of temperature. It's very, very hot.
Oh. But last year summer also it is too hot, right?
Sorry?
Last year summer also it is too hot, right?
Oh yeah, last year too. Yes, yes, yes. Everybody is now speaking about the global warming, and because you know this is the very first time that we can see such temperatures. Records are broken now systematically. It is very strange, and particularly at that time, mid-September, it should not be like that. We have a very hard sun.
Last year, sometimes the temperature will be 40 degrees, something like that.
Yeah, last year.
Last year.
Last year, yeah. Last year it was, I can remember that during the summer it was hot during a very, very long time, and many plants in gardens died because of that, actually. And in Paris, you know, we are rather used to raining, but not to sun. I saw Enrique Zoisois gave a seminar a few days ago, right?
Yes, the last Tuesday.
Last week, yes. Yeah, I could see some pieces of his speech on YouTube.
Yes, it is there. I mean, we generally put it after the talk.
Yeah.
The functional speaker. So that's many people. It's a semester time. So many students say that it will be very useful if you can upload it on the. If they can hear it later on.
Yeah, it's very convenient what you are organizing. Yeah. So systematically, you record the talks by Zoom, and then you put them on YouTube by yourself, or is it automatic?
No, for example, we record it on YouTube. So
yeah.
They have and generally we send it the link. We upload it later to the web page.
Yeah. It's well organized. Yeah.
Yeah. So, Professor Trela, should we start?
Up to you. Yeah. Okay. I'm ready. Yeah.
Okay. Okay. So let us start. So on behalf of the organizers, a very warm welcome to Professor Emmanuel Trelat and to all the participants of webinar on PDE and related areas. For the participants, we request you to keep your questions stored in the question and answer box. Now I kindly request Shishendu Chaudhary to take the session forward.
Thank you, Prashanjit. So we are honored to have Professor Emmanuel Trela with us today. Professor Trela obtained a doctorate under Professor Bernard Bonnard at the University of Burgundy in 2000. From 2015 to 2019, he was the director of the Foundation Sciences Mathématiques de Paris. Currently, he is the director of the Laboratory Jacques Lyons, Paris, France. His research areas are partial differential equations, control theory in finite and infinite dimensions, sub-Riemannian geometry, image analysis, shape optimization, and best actuator and sensor shape locations. He is also a specialist in numerical methods in optimal control and particularly in aerospace applications. He has been awarded the Grand Prize Madame Victor Nouri in 2016, Blaise Pascal Prize in 2014 from Academy of Science France, Felix Klein Prize from European Mathematical Society 2012, and Siam Outstanding Paper Prize in 2006. He was an invited speaker at International Congress of Mathematicians, ICM, at Rio de Janeiro 2018 in the section on control theory and optimization. Today, he will be speaking on sparse control and stabilization to the consensus of collective behavior models. I hope you will enjoy the talk of Professor Emmanuel Trela. Professor Emmanuel Trela, it is over to you now.
Thank you very much, Shershendu. Thank you to all of you for your very kind invitation and to give me the opportunity to report on a series of works that I have done with quite many authors, as you can see, among them actually many Italians. By the way, many Italians working outside of Italy, like often for the Italians. And our objective is to work on collective behavior models that have become quite popular in the 10 last years or so, and to try to do some control on them. Let me explain. So there are in the literature many models, many mathematical models that try to explain the collective behavior of a group of agents. It can be people, it can be birds, it can be fishes, it can be sheep, or it can be also opinions on Facebook or something like that. Well, you have a group of agents that is evolving according to some laws, having some interactions, and these models try to explain the possible self-organization of the group, and also maybe the emergence of a consensus. Consensus means, for instance, all people think in the same way. All birds fly in the same direction. There on the left, what you can see is rather what we call a mill, something which is turning, right? But mill is also a kind of consensus in some sense. All fishes are swimming, let's say, by turning around. This is a mill. So many models in the literature try to explain such the emergence of such behaviors. These can be models in finite dimension, when there are not so many agents, and when the number of agents is so large that maybe you can think of an infinite number of agents, you are going to PDEs and to models in infinite dimension. And so our objective with my co-authors is to try to put a control in such models, like, for instance, you put a dog in order to try to control a flock of sheep. And with such a control that you add, you would like to try to control the group, maybe to try to help, to facilitate, to promote convergence to consensus or something like that, or maybe to try to stabilize the group, or maybe to create clusters, or at the contrary, to decluster people. Everything that you want to make with a control. So to explain what we did, let me introduce the very celebrated Cucker-Smale model, which is certainly prototypical. It was introduced in 2007 by Cucker and Smale, and it is a very simple model in finite dimension, already rich enough to explain many possible phenomena, many interesting phenomena. So this model in finite dimension is very easy to explain. You see that you have a capital N agents. Each agent.
Excuse me, Professor Trela. Did you change your slides already?
Yeah. I'm deleting my slides. You cannot see them?
No. We could not. It's not changed.
Oh, I'm very sorry about that. Let me try again. Can you see the slides now?
Yes.
Oh, so probably you maybe didn't see the previous slide there, right?
Yes. No, we did not see. We only saw the first page.
Oh, you did not. So you did not see my beautiful figure of fishes there.
Yeah.
Okay. So let me. It's not a problem. Let me come back. I'm sorry for that. let me come back to the Cucker-Smale model, which is there. So as I was saying, this is a model describing the evolution of capital N agents. Each agent, let's say, has a position, xi of t, which is evolving according to the speed of the agent, xi dot equal vi. And then vi dot is equal to something that you can see there. And this, what you can see at the right-hand side of vi dot, is a force of attraction. As you can see, you sum over all agents a potential times an attraction force, which is Vj minus Vi, right? So it is a very, very simple model in finite dimension, but already very rich. And actually, it was introduced by Cucker and Smale in 2007, actually in order to describe the formation and evolution of languages in populations. But there you can think of xi as a position and of vi as a speed, because it is easier for the intuition. Such models, by the way, admits generalization. You can put there a general potential. A here is a non-increasing positive function. Well, what is important is that when two agents are far one from each other, you can think of this potential as going to zero. I mean, when you take two agents, two birds, for instance, which are very far one from each other, then we can say that they do not interact because maybe they do not see each other. At the contrary, when the birds are sufficiently close to each other, then the potential enters into play, it is not zero, and then you have an interaction and you have a force, let's say, of attraction or maybe of repulsion, right? So this is the Cucker-Smale model. But there are many, many variants, in particular in social dynamics. There are many variants of such Cucker-Smale models in the literature. It is also interesting at this point to see how the model can be written when you go to the limit. I mean, when capital N tends to the infinity, then you pass to what is called the mean field limit. It has become very much popular also in the 10 last years. And then by taking the mean field limit, you obtain what is called, what we call the kinetic Cucker-Smale model, which describes, as you can see there, the evolution of a probability measure, mu of t, which may have a density. In that case, the density of mu of t is just the density of the crowd taken at some point xv. And mu evolves according to this PDE that you can see there, which is a kinetic partial differential equation, in which, in the divergence term, you can see the interaction kernel, xi of mu, inside of which you recover the potential of interaction, right? And actually, this is by now well known, how to pass to the mean field limit and how to come back to finite dimensional model. The link with finite dimension is quite immediate. When you want to go from infinite dimension to finite dimension, you just have to plug into your PDE the so-called empirical measure, which is a sum of Dirac, right? And if you plug this mu in the PDE, then you exactly recover the finite dimensional Cucker-Smale model that I was showing you before. And in the converse way, if you want to solve the PDE from the finite dimensional model, then you consider the flow that I like to call the particle flow, phi of t, which is the flow corresponding to the finite dimensional Cucker-Smale model. And then the solution of the kinetic Cucker-Smale PDE is just the push forward under the flow phi of t of the initial measure. Okay, so all of that is very well known. This is the link between finite dimensional models and the infinite dimensional model when you take the mean field limit. So it means that in all what I will say next, I will always consider in parallel the case of the finite dimension that you can see to your left and the case of the infinite dimension that you can see to your right, because more or less you have almost the same result that you can obtain exactly by the process that I was describing. So let me make first preliminary remarks on the Cucker-Smale model. So on the left, you have the finite dimensional Cucker-Smale model. On the right, you have the infinite dimensional Cucker-Smale model, which is the kinetic PDE. And the very first observation that we can make is that, well, if you make the average of the positions that I call x bar, if you make the average of the speeds vi that I call v bar, then you immediately observe that v bar is a constant. You just have to sum all equations vi dot to observe that it is 0. So v bar is constant, and you have that the derivative of x bar is just equal to v bar. So it means that the average speed in the Cucker-Smale model is constant, right? This is perfectly intuitive. The second remark is, well, let us make a bit of statistics in some sense, because we are looking at, let's say, a large crowd of people. So in statistics, you often take the variance, and we can take here two variances. The first variance is the variance of the positions that we call capital X. So capital X is the variance of the positions. Capital V is the variance of the speeds, right? And what you can very easily observe is that the time derivative of the variance V has this expression that you can see there at the bottom left of my slide. You can see that V dot has a nice expression, which is always non-positive. So what does it mean? It means that whatever you will do, the variance of the speeds of the group is decreasing, which means that if you wait in time, then the group tends to decrease the distances, the mutual distances between the speeds. So what you would expect is maybe that v of t decreases to 0, converges to 0 as time t tends to infinity. But well, it is not always the case. But this brings us to the following definition, that when the variance capital V of t tends to 0, then it exactly means that all speeds vi of t converge to the same speed, which is the v bar, which is the average. And then we speak of convergence to consensus, or convergence to flocking, right? So you have a group of people, think of birds, all flying in different directions. And if you wait sufficiently, then at the end, all birds fly in the same direction. We speak of a flock, which we speak of convergence to consensus or flocking, right? So now the question is it completely automatic that you have convergence to consensus? And the answer is no, not necessarily, because look at what is written here at the bottom. You have an inequality on V, which is V dot less than something times V of t. And the something that you can see appear here depends on capital X. This is A of capital X or something like that. Well, so actually what this inequality implies is that whenever capital X remains bounded, then in that case, you have an inequality like V dot less than minus V, which implies convergence to 0 and flocking. So what does it mean? It means that if you take a group of birds of which the variance of position is bounded, so take some birds which are, let's say, confined in a compact space, then if they obey to these equations, you have automatically convergence to flocking. However, if the group is not compact, This is perfectly intuitive. If you take two birds that are very, very far one from each other, then they do not see each other because the interaction potential is too weak. And in that case, they will fly without seeing each other. You don't have convergence to consensus, right? So this explains perfectly this proposition, which in finite dimension is due to these authors, Ha and Kim, in 2010. It says that whenever a specific inequality is satisfied on the initial group of people, I mean, if the initial group of people is sufficiently compact, this is something like that. If you are in some region which is here in gray, a favorable region, then whatever you do, you converge to consensus. And this is what people have called self-organization of the group. I mean, it's perfectly intuitive. You take birds, birds are sufficiently close one to each other, or maybe they already fly almost in the same direction, then you converge to flocking, right? Without doing anything. This is a kind of stability region. This is just a stability region in dynamical system. And of course, you have the same result at the level of the kinetic PDE. Well, so now what we would like to do is add a control in the equations, because as we saw, you do not converge necessarily to flocking. If you have a group of people, for instance, let us take two clusters of birds, one there and one there. And if they are sufficiently far one from each other, they do not see each other. So they won't merge. They won't merge naturally. So what we would like to do is add a control in the equations, which is here in red. And with, let's say, nice controls, with good controls, we would like to promote consensus. This is exactly like if in practice, you take a flock of sheep there, and you add a control, and the control here is a dog. And with the dog, which is the control, you would like to control the flock of sheep, maybe to keep it compact. You do not want sheep to travel to infinity, right? You want to keep the flock. This is controlling a flock. So what we simply do in the controlled Cucker-Smale model is add a control in the additive way here. So for the moment, we do something which is quite stupid. We take each equation, vi dot, right? And we add a control in each equation. So it's a kind of stupid because you have capital N gens, right? And we add capital N controls. Okay, so it is as if we had capital N sheep, and we are adding capital N dogs, which is stupid. Of course, the system will be controllable because you have, for one sheep, you have one dog. So it's completely clear, right? So anyway, what we want to do is sparse control. So let me explain. We want, so the control U of t has capital N components. U is a vector having capital N components. And what we would like is that at each instant of time, we would like the control to have maybe at most one active component. Okay, so for every time, we would like all ui of t to be equal to 0, except maybe 1, which would exactly mean that we have one dog, and the dog will act on such or such sheep. And this notion is exactly the notion of what we have called at that time the sparse control, right? So we want, this is the objective, we want to design a control that at each time, at every instant of time, has a minimal amount of components that are active, right? And this is actually what we have called the component-wise sparse control. Okay, so this notion will exactly reflect the fact that in a flock of sheep, we have introduced exactly, let's say, one dog. And maybe at some point, the dog will act on the sheep number 1. At another time, maybe the dog will switch and will act on the sheep number 10, and so on. This is the concept of component-wise sparse control. Also, what is desirable is to have a control that will be time sparse. That is, maybe we would like a control that does not switch so often, right? We do not want a control to be switching very widely. And third requirement, we would like the control to be a feedback control in order to control our group. So how we will do that? So let me explain. Also, the notion of sparse control can be also modeled at the level of the PDE. Well, at the level of the PDE, the control is, let's say, a subset depending on time, small omega of t, on which you can act on the crowd. Because now the crowd is modeled by a density. Take a density of fishes, for instance, and there, somewhere in the domain, you add a subdomain, depending on time, on which you can act. So this is exactly, the dog has become a subdomain, which is time evolving. This is the concept of sparse control at the level of the PDEs. Right. So how will we do that? Well, let me make a first remark. Take our controlled Cucker-Smale model. Then there is a very trivial way to stabilize it to consensus, which is to take a full control, which is the full control which is written here. So this control, as it can be obviously computed, stabilizes the system to consensus, but it is a stupid control because this control is full. Every component of this control at every instant of time is active. So it is not a good control. This control is far from being sparse. It is a full control. It is not a good control. But this control is just at least to ensure that indeed the system is stabilizable. So what I say here is that you have n sheep, you take n dog, and so the dogs can control the group of sheep. This is obvious, right? But this is anyway the first mathematical remark. Now, how from this obvious control, how can we design a sparse control? Let me make the remark. Well, actually, what we can observe is that this full control can be obtained by a minimization procedure, which actually consists of minimizing the v dot term, as we will see in one moment. Well, but you know, some 15 years ago or some 20 years ago, something like that, there was the appearance of sparsity in imaging. And the main idea of which was raised at that time, in particular by Terence Tao, as you know, also by Emmanuel Candes, was to say the following. It's a very, very simple problem of optimization. The problem is the following. Take a linear functional, and you want to maximize a linear functional over the unit disk, right? So depending on the slope of your linear functional, of course, the maximum is always attained at the boundary of the ball, okay? And the optimal angle can be arbitrary in function of the slope of the linear functional, right? Now, if instead of looking at the unit Euclidean ball, I look at, according to the idea by Candace and Tao, I look at the L1 ball. So the unit L1 ball is, as you know, this square. And now let me maximize a linear functional over the L1 unit ball. Then what you obtain, as you can see, what you obtain is that systematically, except maybe at degenerate situations, systematically the maximum is reached at those black points, which are the extremal point of the L1 ball, right? This is an observation in optimization that has reached to the by now well-known L1 optimization theory. So it says that if in some minimization problem you are adding a penalty term, a penalization term, which is a L1 norm, then you will expect that the optimal solution is sparse. It's sparse, why? Because here the optimal solutions are sparse because they are exactly along the coordinate axis, right? So exactly one component is active and all other components are equal to 0. So this is a very simple but illuminating idea that was very, very much used in imaging. So this is also the idea that we use here. The general idea, intuitive, is put some L1 norm in an optimization criterion, and then you will promote sparsity. So this is what we do. And indeed, solving this problem, we exactly obtain what we want, that is a component-wise sparse feedback control that stabilizes the system to consensus. So it is indeed component-wise sparse. I mean, at every instant of time, at most one component of the control is not equal to 0. So this is the property that we wanted to achieve. And moreover, even better than that, actually, we even have a stabilization to consensus in finite time, if we want. Because if we plug the control that we have obtained in the V dot inequality, what we obtain as a new inequality now is V dot less than minus square root of V. And so if we solve this inequality, then we obtain that capital V of t converges to 0 in finite time. This is great. I mean, with this feedback and sparse control, we can realize, if we want, stabilization to consensus in finite time. Well, actually, this is probably not what we will do in practice. In practice, what we will do is, let's say start from an initial position, letting the control act. And once we are in the consensus region, which is the natural stability region, we switch off the control and we let the system converge to the consensus in infinite time. This is probably even a better strategy. Okay, let me switch that. And actually, moreover, this feedback control that we obtain actually minimizes the V dot over all possible feedback controls. What I mean here is that among all possible feedback controls that you can try, this feedback control that we have chosen here is in some sense the optimal choice in terms of the instantaneous rate of convergence to consensus. So, and probably this is a kind of counterintuitive, because what we underline here is that in some sense, sparse is always better. Let me explain intuitively what this principle is saying here. For this model, imagine that you have an amount of money to distribute to people, right? Because you want to steer a group of people to some, let's say, to some consensus, right? And you have an amount of money, you have an amount of projects, for instance, to give to people at the university, right? I will say something that is not politically correct. Then what this principle says here is that the best policy is to give all the money to only one person. And it is better to give all the money to only one person. It is better than giving a small amount of money to everyone. So this is why it is not politically correct. Okay, but certainly this observation that sparse is better is fully attached to this Cucker-Smale model, and I do not advise that it would be applied in politics, right? It is probably not so good. Okay. The same observations can be generalized at the level of the PDE, I mean to the kinetic Cucker-Smale equation. However, when, as you can expect, when you are working on the PDE, well, you have to be extremely careful with the problem of existence of solutions. In particular, since here you take the divergence of a measure here, you should ensure that along time, the probability measure remains absolutely continuous. Because if the measure reaches a Dirac in finite time, then this PDE does not make sense anymore. So I will not at all enter into such mathematical problems, because actually these are purely mathematical problems that do not so much reflect what happens in reality. But anyway, what I can say here is that there are some mathematical traps. And so we have to slightly adapt our control strategy in order to keep the probability measure absolutely continuous. And actually, this is a non-obvious point in our proof to steer to consensus the kinetic Cucker-Smale model. But anyway, what I can say is that at the very end, at the end of the day, we have a perfect commutative diagram between control on the one part and taking the mean field limit on the other part. What I mean here is that at the beginning, we took the finite dimensional Cucker-Smale model. Let us say you take capital N particles that are interacting. What you can do for this finite dimensional model is add a control in it. This is what we did. Or you can also first take the mean field limit in this crowd of capital N particles, and then you obtain a non-local transport equation of the divergence kind, right? Now you could do also the converse way. You could take directly the PDE, which is here, and try to add a control inside, which would give you the controlled non-local transport equation that is written here. The question is, would this diagram be commutative? It is not at all obvious. It is not at all obvious that if you pass to the mean field limit in this controlled finite dimensional model, you will obtain exactly what you would obtain by controlling directly the kinetic PDE, right? It is not obvious. It is not obvious that this diagram is commutative. And by the way, in general, if you take completely arbitrary controls, this diagram is not commutative. But what I claim is that with the feedback sparse control that we have taken here and that I have shown you, this diagram is commutative, right? So it makes sense. It makes sense to let the number of agents tend to the infinity, in some sense, to be well precise in our sparse strategy. This is my claim. Let me show you several numerical simulations just to have fun. So take birds. Take birds, and these are the initial conditions for the birds. So you are taking here 3 birds that initially are flying to the same way, right? And you take a 4th bird here that is flying in another direction, right? And what you want is act on this crowd of 4 birds and try to bring them to consensus. So let us implement the sparse control that we have designed, and it gives the following simulation, right? So in green, you have the instance of time where we are acting on the bird, right? So you recover here the 3 birds that were flying in the same direction. Here, the bird that was flying in the orthogonal direction. This trajectory that I'm showing here would be the natural trajectory. I mean, when there is no control. So when there is no control, the bird is bending a bit its trajectory because of the interactions, but you see that you do not converge to some flock. The 3 birds continue their way, and the orthogonal bird is also continuing its way. But if you activate the control, so here the green part is the activated control. So you are acting on the orthogonal bird, you bend its trajectory, and you see that at the end you have obtained consensus, because at the end the 4 birds are flying in the same direction, right? So let us now take, let's say, 5 birds. So you take always the 3 birds flying in the same direction. You take the orthogonal bird, and now you add a new bird that is flying exactly in the converse way, right? You know, it is like, you know, when you are in a meeting with people and you want, let's say, to convince people that you are right. You want to steer people to your opinion, right? This is exactly converging to consensus from the point of view of opinions. So here I am figuring out that you are in a room, 3 people, let's say, agree with you, and there is a person that completely disagrees with you, right? You all experimented that situation, I guess, right? So what will you do intuitively if you want to convince all the crowd of people in the room that you are right? Very certainly, at the beginning, you will concentrate your convincing efforts on that guy, the guy that is thinking exactly the opposite, right? You will concentrate your efforts on this guy. This is exactly, actually, without any surprise, this is actually what we are doing. Let me show you the simulation that will show you that indeed we essentially concentrate the control on that bad guy, the guy that is thinking at the opposite of you, just to bend his opinion and make him think exactly like you. Let me show you the simulation. You see, you concentrate the effort on the bad guy or the bad bird, except maybe at some point. But essentially, you see that you concentrate on it. And at the end, you see that, again, all birds fly in the same direction. Consensus has been reached, right? So you have been successful in your meeting, I hope. Okay, so this was only for a very low number of people, but of course we can take many people, many agents, For instance, here I took 20 gens, which is still not many, but this is just so that you can see something. Otherwise, we do not see anything. So you take 20 gens, of which the initial speeds are completely arbitrary there. And let me launch the simulations. So here, since the speeds, the initial speeds are a bit arbitrary, probably the control will very much switch from one to the other agent, because you will have to act on many agents. So you will have to switch a lot. This is not a surprise. And indeed, let me show you the numerical simulation. So you see that there are many switchings. And these are the points in green. But what is important is that at the end, it converges. At the end, all birds are flying in the same direction. Or maybe all sheep. And it could be a flock of sheep, completely disordered, and you put one dog, and the dog has to switch very much between each sheep in order to bring the sheep to a flock, to a nice flock. Right. Let me make some additional remarks on several things that can be also said. From the point of view of controllability, what can be proved theoretically and in finite dimension only, because I do not know how to prove it in infinite dimension, you can prove local controllability properties near consensus for the finite dimensional Cucker-Smale model. This can be proved. But an open question, I do not know how to address that question, is how to establish local controllability properties for the kinetic Cucker-Smale model. I do not know. I do not know the answer. So the open problem is how to establish controllability properties for this kinetic divergence-like PDE. I do not know. This I will switch. What I would like to mention is that also with my Italian colleagues, we have by far generalized the class of system to which we can develop a sparse feedback control strategy. These are actually all control-affine systems in a finite dimension that are so-called dissipative, and their mean field version. And we have developed what we have called a sparse Georgievic-Quinn strategy. What I will only say without entering into details is that this class is very large, because this class of systems involves Cucker-Smale models and many variants. It also involves you know, the well-known Exelman and Krause models, which are very popular in social dynamics and also in Automatica. In Automatica, there are plenty of papers on the Exelman-Krause models, which enter also in our theory here. And what we have been able to design, to conceive, is some feedback controls, so still sparse, that can steer this kind of system, for instance, either to consensus, full consensus, or maybe to clusters. As an extension, so there are many possible generalizations of such models. Here is one possible generalization. You can put some delays in the model. For instance, imagine that you look at your neighbors, but there is maybe a delay in the signal that is propagating. So we have done this kind of study with Cristina Pignotti. We can generalize the class of potentials, and there is a very interesting generalization that I can show you. We are currently working actually with Carrillo, Calizet, and Rossi about the control of a model that is due to Bertozzi, Chayes, Chuang, and Dorsonia, which is this finite dimensional model that you can see is different, is quite different from the Cucker-Smale model. And so we add control in this model. You can see that this model, mainly there are two terms here, the red and the blue term. The red term is promoting self-propulsion of the agents, and the blue term is promoting attraction and repulsion forces due to a potential W. Well, the main interest, I find, the main interest of that kind of model is that when there is no control, and these are studies by Andrea Bertozzi in particular, then there are some particular configurations that are solutions of the system, which are exactly what I said at the beginning, meals. So a meal is this configuration that you can see at the bottom of my slide here. You take, for instance, fishes that are, you know, in the sea, in the oceans, fishes that are turning around and around. This is what we call a meal configuration. And what is very, very interesting is to try to act on such meals. So what we are currently finishing to prove with Carriot, Calizet, and Rossi, by combining various techniques, and in particular dynamical systems strategies, we are showing that such systems are controllable either to flux or meals. So this is very interesting because for the first time here, we are able to control meals, exactly like do dolphins in oceans. You know, dolphins are controlling meals of fishes in a very, very nice way. Can you see the video I opened? Yeah. Can you see the video I opened or not?
Not
really. Not. Okay. So sorry. Let me stop sharing my screen one moment, and let me try to do like that. Probably. Can you see it now?
Yes.
Oh, very good. Very good. So what you can see here is many fishes. Actually, they are already in a meal configuration. They are turning around and around. And there, what you can see is dolphins. So exactly like a dog with a flock of sheep. It's exactly similar. And as you will see on this video, dolphins are controlling meals in a very, very nice way. Let me show you. So you see that dolphins are exactly acting in order to control the meals. As you can see, they do that very, very well, much better than we would do, of course. This is nature, right? So this is a very usual game for dolphins to control, to act on meals of fishes. And this beautiful natural phenomenon is exactly what we try to reflect here in this model with Carriot, Calizet, and Rossi. Right. Can you see my slides again? It's okay. Yeah. Okay. Okay, and as a conclusion, so we can do many other things by working on interesting variants. What we can do also is try to decluster. Well, I'm laughing, but it's not. I should not laugh. With the current pandemic situation, declusterization has become a bit fashion in some sense. But well, actually, without knowing about the pandemic, of course, with Benedetto Piccoli and Nastasia Pouradier-Dutaille, we have addressed this problem of declustering crowds of people thanks to control. We have addressed it some time ago. And we can do many other things. What I have never addressed, for instance, is try to address stochastic models from the point of view of controls. This has not been done until now, to my knowledge, but there are certainly very interesting questions to be addressed here. And also, and I will finish with that remark, there are many other ways of passing from finite to infinite dimension. In this talk, I have shown how to pass to the mean field limit, which is very popular. But there are other ways, such as, for instance, hydrodynamic limits, which are well known in fluid dynamics, for instance. The question would be, the question I have in mind there would be, would we able to control a fluid just by acting on several particles of fluid and then try to pass to the hydrodynamic limit? I think the procedure is probably quite similar to what we did here, but it's, according to me, so there are many open questions, but this is here one of them. And I will finish with that observation, and I thank you for your attention.
Thank you very much, Professor Emmanuel Taylor, for such a lucid talk. So we have received some questions from the participant. I'm conveying to you on their behalf.
Okay.
So are these sparse control unique? If not, is it possible to introduce some cost, say switching cost, and to select an optimal control?
Yeah, it's an excellent question. Thank you for the question. So first of all, no, they are not unique. There is no unique way of sparsifying a control. There, the way we sparsify is by using a penalization by a L1 norm. But of course, there are many other ways. For instance, we could penalize by a LP norm with P less than 1. This would give slightly different controls that would also be sparse. So, but you asked the good question, because then how to discriminate, how to choose a good sparse control, and your question is, can we put some cost? And indeed, it's a very, very good idea. And for instance, a good cost to be considered is then the number of switches. Because as you could see when I took many agents, 20 or 50 agents, you expect that the control will have many, many switchings. It's very easy to understand. You take a crowd of sheep, but which is completely disordered. Your sheep are doing anything. They are going in each way. And imagine that you have only one dog in order to control, let's say, 50 sheep. So the dog will have much work, of course. The dog will have to jump from one sheep to any other very, very quickly. This exactly reflects the fact that the optimal control will switch very much. And this is exactly a good notion of a cost, because it means that, at least for the dog, the cost of controlling the crowd is very large, right? While, of course, we could ask the question of trying to control the crowd, if this is possible, with a minimal number of switches. But there it is not always possible. As you can imagine, the intuition says that there should be some limitations, right? But so the answer to your question is no, there is no unique sparse control. And yes, we can put some cost on sparse controls, like, for instance, the number of switches or something like that, which is, in my view, a good cost in order to measure some complexity.
So there is another question. It appears to me that consensus leads to the equilibrium of velocity V bar. How about the state convergence? There is the convergence of X. Is it obvious?
So consensus on the Cucker-Smale model was defined in some sense in a quotient space. I mean, you are right, all VI's are converging to the same value, which is V bar, and then all Xi of t are converging to some trajectory, which is a straight line. Because when you have reached the consensus, then for every I, you have Xi dot equal V bar. And hence, Xi of t at the limit is equal to V bar times t, which means that all birds are moving in the same direction. So it is a motion of translation, right? So actually, it's a kind of equilibrium, but in order to give a sense to the word equilibrium, you just have to take the quotient by translation geometrically. And for the meal configuration, I mean, birds or fishes that are swimming this way, then in this configuration, you have to take the quotient by all possible rotations to give a sense to the notion of equilibrium, right?
So we have another question that in one of your slide, why the restriction for beta is strictly less than is required. So
Sorry, I didn't understand. Sorry, can you repeat?
So there in your slide, it is somewhere that why some restriction on beta is given.
Oh,
so written that why the restriction on beta is less than is required.
Okay. This is because I did not comment on this beta. So this was, where it is. It's there. Yeah, it's there. I think it's there. Well, this was an initial observation by Cucker and Smale in 2007 that if in the potential that they do consider in their paper, if the parameter beta is less than 1/2, then automatically you have convergence to consensus, and this is completely global. What I mean is that, let me switch to this slide. This means that the consensus region that is in gray here is actually the whole space. Okay? So if beta is less than some threshold, 1/2, then whatever you do, you always have convergence to consensus. But if beta is greater than 1/2, for instance, beta equal 1, then you have a region of stability which is a compact one. And outside of this stability region, you do not have a natural convergence to consensus. And this is why doing control is interesting on that kind of data.
So we have another question that if we use a penalization with P strictly less than 1 instead of L1, convexity argument for getting the minimum may not work. How does one guarantee infimum in that case?
Oh, I do not know. I do not know. It's a good question. This is my guess that probably the optimum should exist, but no, I do not know. I do not know. I did not study that. I did not study. This is only my guess. But so my guess is that the minimum still exists. At least I hope so. And if it still exists, then it should be sparse because the unit bore, you know, is something like that. Okay, with a kind of cusps like that.
So there are two more questions which is in the personal box. One is, can we say something about the regularity of the solution? Say if we take the initial condition as Gaussian distribution, will the solution be Gaussian for all time?
You mean on the infinite dimensional kinetic Cucker-Smale?
Yes.
Yeah, we have proved this fact, yes. And precisely, well, this kind of fact is the non-obvious part of our proof. Yes. It does not work. I'm not saying it works for any control. It works for the control that we have designed. Otherwise, actually, what we are able to prove, it has no interest for the study, but we are able to prove that whatever the initial condition may be, so for instance, you take a Gaussian, well, I claim that there exists a control strategy that steers the system to a Dirac in finite time. Okay, and so it has no interest, because as soon as you have reached a Dirac, then the equation makes no sense anymore. Mathematically, there is a serious problem there. So at the contrary, the good strategy is instead to be able to design a control that will keep the measure absolutely continuous as much as possible. In our strategy, the probability measure becomes singular, yes, but in infinite time, which gives some sense to the mathematical equation. But you are right to ask this question, because it is there is a serious difficulty with the existence there, and it is quite technical in our article. It is a quite technical point. Yeah.
There is another question is written that, is there any relation between the weak convergence of measure with the convergence of consensus?
So convergence to consensus at the level of the measure exactly means indeed that the mu of t converges weakly to a Dirac. Probably I have, let me show a slide. Oh, I have an, oh no, it's not there. Yeah, it's more or less written here. It's more or less written here. Yeah. Convergence to consensus is defined here. Okay, and actually this means, roughly speaking, that mu of t, the measure mu of t, converges weakly to a Dirac in V. This is the meaning.
So if the participant has some more questions, they can ask directly, or they can write down in question answer box.
Of course, I'm also open to electronic questions by email. And if you have further questions, don't hesitate to send me an email. I would be very, very happy to try to share some open issues with one of you.
So I have a question in this case. So that means, see, due to this one, since you are switching, so in this situation, getting some kind of a control is somewhere discontinuous, right? Because of this switching. So you can get is we able to reach this kind of consensus with a smooth control? Is it possible?
Oh, it's a very good question, Shirshendu. Yes, because if you are figurating the practical situation of a dog with sheep, letting the control discontinuous means that the dog would jump instantaneously from one sheep to another, which is of course not possible. In practice, the dog cannot have an infinite speed, right? It's only a mathematical model. So in practice, it means that you would have to add a finite velocity for the dog, which is actually equivalent to smoothen the control. It's more or less equivalent, as you can see. But if you add this restriction, then you also understand that it is not always possible to steer any group of people to consensus. right? Because imagine that you have sheep that run very, very quickly. So you have a sheep there, and they run very, very quickly. Then whatever the dog will do, he cannot bring the sheep to a crowd because there is a limitation on the speed of the dog, right? So either if you ask to smoothen the control, let's say reasonably, with bounds on the slopes, for instance, or if you add some finite speed on the control in some sense, like the dog, then you have limitations on what you will be able to do. But it is completely natural. So this is not the situation that we have written in our papers, because we have written the purely mathematical situation where, in some sense, the speed of the dog is infinite. It's a quantum dog in some sense.
And another thing that you have defined some region of consciousness. So can you show the slides? You have some inequality through A, right? Some integral inequality.
Integral inequality on the variance, you mean?
No, the region you define, region of consensus. Can you show the slides there?
It's this one, right?
Yes. So my question is that this, you told that this is the region, it shows that where already, if I choose any data, it will go to consensus, or this one. So that means if is something that if this x0 and v0 is somewhere small, then, and this integral is, suppose this integral is infinite in some way, depending on A, so then it will be satisfied, right?
I'm sorry, I didn't understand what you said at the end, Cherchendu.
Yes, so I am asking that, is it means that x0 and v0, if you take a small, the norm is small. In that case, is obvious for.
In that case, it's the inequality there is obvious. Yeah, it is satisfied. You are right. Yes.
And that means that depending on the A, if the integral is somewhere infinite, if for this A, then it will automatically satisfy it.
Oh, yeah. But this is exactly the meaning of the question about beta, because indeed, when this integral diverges, then this inequality is always satisfied. You see, this is why we recover the result by Cucker-Smale in 2007. When this integral is diverging, I mean it is equal to plus infinity, then this assumption is automatically satisfied and you always have convergence to consensus. This is right. Actually, this also reflects something which is very intuitive. If the potential is strong enough, I mean here it decreases, but not so much. In that case, if you take two agents that are very far one from each other, if the potential is strong enough, they can see each other. And so they do interact. Otherwise, if you take a potential that is strongly decreasing, or maybe even a potential that has compact support, then in general, you will expect that this integral is finite, right? And in that case, of course, you expect that there is a requirement, a condition, in order to ensure the natural stability. This is just a matter of the potential. Well, so of course, in many practical situations, we always consider potentials that are functions that have a compact support. And the size of the compact support is called in social dynamics the sphere of influence. There is a sphere of influence. So you take an agent, and an agent has a sphere of influence. I mean, the agent is able to act on such or such people within a certain distance, called sphere of influence. But if some agents are too far, then you cannot act on them. You do not see them. You cannot influence them.
So that means the interaction is small in that case.
Interaction is small or maybe even equal to 0. Yeah. Yeah. And this is why, by the way, clusters can emerge. In a cluster, you have a stability, a local stability. In another cluster, you have another local stability. But in some sense, the two clusters cannot see each other because the interaction between them is either too weak or maybe is equal to 0.
And just one more question related that functional you define. In that you have some kind of the function is also involved this quantity like gamma. I saw something in the cost functional with a coefficient, which is gamma of x something.
Let me go to it. So gamma, yes, this gamma, yes. Gamma is a kind of weight that we choose in the penalization process. It was also a choice that will then ultimately lead to a nice expressions for the feedback control. But as we discussed previously, there is not a unique way to obtain a sparse control, and there you can make some choice. And there we make a specific choice for the weight there that we put in front of the L1 norm. But actually, this weight is not very much important.
Is it that this weight when this gamma x is greater than that V0 or something you show in the earlier slide, then you will stop?
Yeah, this is exactly that. This gamma of x has an interpretation in terms of the natural region of stability. Yes. Yes, exactly. Exactly. Yeah.
So, thank you, Professor Emmanuel Trela, so making this session successful. We hope to get your participation in future talk as well. Prosenjit, it's over to you.
Yeah. So to the participants, last few words. We hope that you thoroughly enjoyed Professor Trela's talk today. So we'll close the session today, and we will meet in next 2 days for Professor Roberta Filippucci's talk on P-Laplacian problem with gradient term. Thank you, Professor Trela, again for such a nice talk. Thank you. So now I request all the participants to leave the platform. Thank you very much.
Thank you so much.
Thank you, Professor Trela, very much.
Thank you again. Bye-bye.
Bye-bye. Let me disconnect the YouTube link. Yes.